Welcome to the Shikasa Boo Motor channel. This channel provides easy-to-understand explanations of car mechanisms. As you may know, there are three types of systems for deceleration in passenger vehicles: service braking, engine braking, and regenerative braking. In gasoline and diesel engine vehicles, service braking and engine braking are used. In battery EVs, service braking and regenerative braking are used. In hybrid vehicles, service braking, engine braking, and regenerative braking are used. The main topic of this video is how a hybrid vehicle behaves when the battery becomes fully charged. But first, let's take a look at each of the braking systems. The service brake is also known as the foot brake, but in this video, we will refer to it as the service brake. This is a system that converts the force applied by the driver on the brake pedal into hydraulic pressure, which then presses the brake pads against the brake discs rotating with the wheels, slowing down the vehicle through friction. From a slightly more physical perspective, the kinetic energy of the moving vehicle is converted into thermal energy by the brake discs and pads, which is then dissipated into the atmosphere. In other words, the vehicle slows down by discarding the energy it gained from burning fuel to accelerate. The driver can easily control the braking force by changing the pressure on the brake pedal. One of the main issues with the service brake is the buildup of excessive heat. When the brake pad temperature exceeds 300 degrees Celsius, brake fade may occur. When the brake fluid temperature exceeds its boiling point, vapor lock can occur. Brake fade is a phenomenon in which overheating of the brake pads causes some of the material on the pad surface to vaporize, forming a gas layer that reduces the coefficient of friction and weakens braking performance. Vapor lock is a phenomenon where heat is transferred to the brake fluid, causing it to reach its boiling point and form gas bubbles within the brake lines. Liquids cannot be compressed, but gases can be compressed. As a result, the force applied by the driver on the brake pedal is not transmitted to the brake pads, and the brakes become completely ineffective. For these reasons, especially when descending long mountain roads, the driver needs to be cautious to prevent the brakes from overheating. Simply put, engine braking consumes the vehicle's energy by making the engine operate as an air pump. Engine operation is divided into the intake stroke, compression stroke, power stroke, and exhaust stroke. When the throttle valve is closed during the intake stroke, a large amount of energy is required because the engine must draw air through a narrow passage. Imagine trying to draw water with a syringe, once with a thin tube attached and once with a thick tube. The thin tube requires greater force. In a simple calculation, a 2.0 liters four-cylinder engine running at 3,000 revolutions per minute requires each cylinder to draw in 500 cc of air in just 0.01 seconds. This requires a considerable amount of energy, and engine braking uses that energy to slow the vehicle down. When the engine speed is increased, more air is drawn in per unit of time, which requires more energy and results in stronger engine braking. For this reason, the driver can control the strength of engine braking by shifting gears. However, since it merely moves air from around the air cleaner inlet to the exhaust outlet, it doesn't generate anything. This channel offers a detailed video explaining engine braking. If you're interested, be sure to check it out. The link is in the description. The regenerative braking used in electrified vehicles, including battery EVs and hybrid vehicles, is highly efficient in terms of energy utilization. An electric motor generates rotational force when electricity is supplied to it. When rotational force is applied to it from an external source, it functions as a generator that produces electricity. In electrified vehicles, the drive motor rotates the wheels using electricity either stored in the battery or generated by the generator during driving. When the driver releases the accelerator pedal or depresses the brake pedal, the drive motor is rotated by the wheels and functions as a generator to produce electricity. The electricity is stored in the battery and used to power the drive motor during acceleration. While surface braking and engine braking simply discard the energy stored in the vehicle during acceleration, regenerative braking recovers that energy and reuses it. For this reason, regenerative braking helps extend the driving range in battery EVs and improves fuel efficiency in hybrid vehicles. For an electric motor to operate as a generator, electricity must flow through the motor. If the circuit is closed to allow electricity to flow, it acts as a generator. If the circuit is broken, it's just a rotating object. In electrified vehicles, the traction inverter controls the electricity flowing to the motor to adjust the braking force. Generally, this is handled by the power unit control system, so the driver cannot control it freely. However, some models are equipped with a feature that allows the driver to adjust the strength of regenerative braking using paddle levers located behind the steering wheel. There is a problem. Regenerative braking works by charging the battery with the electricity generated by the motor. What happens if the battery becomes fully charged? In hybrid vehicles equipped with only a small capacity battery, this situation can occur when driving down a long mountain road, for example. At such times, the power unit control system uses engine braking. Let's start by taking a look at how Toyota's power split hybrid system works. Depending on the market, it's called Synergy Drive or THS2, but essentially, it's the hybrid system used in the Prius. This system consists of an engine, a planetary gear set, motor generator 1, primarily responsible for generating electricity, called MG1, and MG2, mainly responsible for driving the wheels. The planetary gear set serves to split and combine the driving force from the engine and two motors, and also functions as a CVT, continuously variable transmission, when the engine is driving the vehicle. This channel offers a detailed video explaining Toyota's hybrid system. If you're interested, be sure to check it out. The link is in the description. When regenerative braking is active, the rotation of the wheels is transmitted to MG2, which generates electricity and produces braking force. MG1 is rotating freely, and the engine is stopped. When the battery becomes fully charged, MG2 operates as a generator, and the electricity it produces is used to run MG1 as a motor. As a result, the reduction ratio of the planetary gear set, which functions as a CVT, increases, causing the engine to rotate at high speed and generate strong braking force. When driving down a long mountain road, the control system automatically starts the engine once the battery becomes fully charged. Since only the sound of the motor had been heard until then, drivers who aren't well versed in the system may be surprised when the engine suddenly starts running. Honda and Nissan have adopted series hybrid systems. In these systems, the engine operates a generator, and the generated electricity powers a drive motor that drives the wheels. Therefore, the engine and the wheels are not mechanically connected. This channel offers a detailed video that explains how series hybrid systems work. If you're interested, feel free to watch it. The link is in the description. When regenerative braking is active, the drive motor functions as a generator, charging the battery and providing braking force. Even when the battery is fully charged, this system cannot mechanically transmit the rotation of the wheels to the engine to apply engine braking. Honda's system includes a mechanism that directly connects the engine to the wheels during constant speed driving on highways, but in the case of the Civic, the reduction ratio is 0.805. The gear ratio is optimized for highway cruising in top gear, and is not appropriate for descending mountain roads. Therefore, in a series hybrid, the generator operates as a motor to rotate the engine, consuming electricity. This is a bit complicated. Let's break it down. The braking force is generated by the drive motor operating as a generator. In order for that to happen, the electrical circuit must be closed to enable current flow. However, the battery can no longer be charged. Therefore, the generated electricity is supplied to the generator operating as a motor. The generator consumes electricity to drive the engine. I believe you now understand that hybrid vehicles have three types of braking systems. The service brake, regenerative braking when the battery is not fully charged, and engine braking when the battery is fully charged. A question comes to mind. What happens with battery EVs that don't have an engine when the battery is fully charged? When going down a long mountain road, relying solely on the service brakes without using regenerative or engine braking can lead to the risk of brake fade or vapor lock.
You can rest assured.
Before you go down a mountain road, you first have to climb it. Battery EVs consume more electricity when climbing than the battery capacity needed for regenerative braking when descending. But what if your home, equipped with a charging station, were located at the top of the mountain road? It might be wise to avoid charging to 100% before going out. Thank you for watching. If you enjoyed this video, please consider subscribing to the channel. We'll see you in the next video.